Hi friends, welcome to my channel. Let's have a look at another unique binary search trees problem, problem 96. In this video, we're going to continue the video on problem 95. In problem 95, we explained how to build all the unique binary search trees by recursion. So this problem here concerns the number of unique binary search trees, in other words, counting. So first, I'll read through the statement to recall the requirement, and then we analyze the problem, and finally we share the code. Here, given an integer n, we are required to return the number of structurally unique BSTs, which has exactly n nodes of unique values from 1 to n. So here are two examples with the corresponding n's and corresponding outputs. So before we do the analysis, let's look at the constraints. So here n is bounded below by 1 and bounded above by 19, right? So this number n itself is not a large number. So with that said, we have a feeling about the problem size. So now let's look at the analysis. So in this problem, so if we understand the construction of unique binary search trees, actually it's straightforward to do the counting. I would say actually these two problems are sort of the same, just one counts on the specific trees and the other here counts the numbers. So here are several points. First, if we have no nodes or just one node, so the number is 1, right? There's only one binary search tree. Secondly, if we have n nodes with distinct values, let's take 1, 2 up to n, for example. Then we could choose any one of the nodes as root. And then let's assume that we choose number I to be the node value as the root. So then we need to use 1, 2 up to I minus 1 to build the left subtree. And we use I plus 1 to n to build the right subtree. So due to the binary search property. So when we build the subtrees, so this procedure recursively continues. So that's the main idea. Now let's look at the numbers. Assume that we have a function f, which if we give a number of nodes, we're going to compute the number of unique binary search trees. So here are actually the recursion relation. So fn is nothing but the summation of the different summation of the product of different left subtrees and different right subtrees. Thus, we have chosen a node with value I. So here, there are I minus 1 numbers less than I. So we have I minus 1 nodes for left subtree. That is f I minus 1. So this is the number of different left sub-binary search trees. So similarly, if we look at the right subtree, so there are n minus I nodes. So all n minus I values greater than I. So this fn minus I is the number of different right sub-binary search trees. So here I runs from 1 to n. So this actually is the recursion relation, or a DP update rule if we want to use dynamic programming. So the next line actually is a change of variable. So if we change the summation with respect to I to be with respect to g, so we let g equals I minus 1. So then this summation is nothing but fg times fn minus 1 minus g. So previously I runs from 1 to n. Now g runs from 0 to n minus 1. So this second equality is meant to make or establish a connection with the Catalan number Cm. So if we look at the second equality, this number is nothing but the Catalan number Cm. So therefore, to get the number of unique binary search trees, here we could do either of the two following treatments. First, we use DP. So this is natural and actually routine if we do not know the Catalan numbers. Secondly, so we can use the Catalan number recursion formula. So the recursion relation for Catalan number, let's use C and n to demonstrate the nth Catalan number. So this writing is just for convenience of writing, right? So here, we initialize a start. So at 0, it's 1, and 1 actually is also 1. Then this is the recursion relation. So with that said, now we can look at the code. Actually, for the code, it's actually very standard and routine. So here, first, I'm going to write a DP solution. For the DP solution, so I'm going to, because it means count, so I'm going to use count, so 0 times m plus 1. So in other words, count I means that if we have I distinct values, how many distinct binary search trees, right? So we are going to return count m, right? So notice that in this initialization, we used a list of length n plus 1, right? So in this case, the last element has index m, right? So count 0 should be 1, right? So if we have no nodes, so this is 1. So now we just need to use the recursion DP update rule here. So now let's do this. Basically, it's a DP update rule or relation. So this is a for loop for I in range 1 up to m plus 1. It means that we choose value I as the root value. And then we're going to add the things together for j in range 0 to I. So let's emphasize this 0, right? So because left subtree can be empty tree. So here count I is incremented by this case, right? In other words, if we have j nodes in the left subtree, and then we have count I minus j minus 1 nodes in the right subtree, right? So this actually this updates it's doing the update according to the thing here, right? So here you can understand that for this I for fixed I, we determine how many different unique binary search trees if we have in total I nodes, right? So what we're going to do to return actually is count n, right? So let's directly return this. So with that said, I guess that's about it for this specific version. So let's do a check. Yeah, it passes the first example. So now let's look at generic case. Yeah, it passes the generic case. So with that done, so let's copy this function signature, and then let's use the Catalan number. So I'm going to call this first version v1. So now let's use Catalan number. So I'm going to use a recursion relation in the sense of mathematics. So we are going to use this formula, right? So here, let me initialize a result variable. So initially 1. Then we are going to iterate n times, right? So for I in range n, right? And then the result equals the previous result times the factor here, this factor. So it's 2 times I plus 1, and the integer division by I plus 2. So once we finish this iteration or for loop, so we can return the result state. So actually, if we like, actually there is a formula for this Catalan number in terms of factorials, like here. So you can do this directly. So you can get more information on Catalan number in this Wikipedia page. So with that said, let's do a check. Yeah, it passes the first example. Now let's look at the generic case. That's about it for the second solution. So I guess that's about it for this specific problem. So here, actually, the version v1 is more natural. So if we do not know the Catalan number, right, in mathematics. So with that said, I guess that's it for this video. Thank you.